So we now want to look at halohydrin formations. We saw halohydrins back in chapter 9 for synthesis of epoxides, but here we want to look at how is it that we make halohydrins. Well, the way that we can make a halohydrin using chlorine or bromine, really only works with those, is that we have a mixture of the halogen, Cl2 or Br2, and water, and that will form a halohydrin when mixed with an alkene. We essentially add the chlorine and bromine to the double bond, and then water comes in and acts as the nucleophile. So when we do this, we're going to break the carbon-carbon pi bond, and we're going to add the halogen to it, and that will form a bridged halonium ion. And again, chlorine or bromine will work. But instead of having the halide, the negative ion that was generated here, instead of having that act as the nucleophile, we'll have water act as a nucleophile, and we can form the halohydrin. So as far as the mechanism looks very familiar because we do form that bridged halonium ion. So we get the reaction with the electrophile halogen forming a bridged halonium ion. And then in the second step, our halide, even though the halide is still a pretty good nucleophile, we're going to have H2O in a much higher solvent concentration. And so as a consequence, it will come in, act as the nucleophile, and do the bridged halonium ion ring opening. And then in our third step, we're going to have a deprotonation of the H2O plus. We've seen this in other reactions where we add H2O across something, or we use it as a substitution reaction. So we've seen this kind of deprotonation. It's just sort of an extra step to get us the neutral compound. We're going to use, sometimes what we can use is N-bromosuccinimide, all right? And it is an effective substitute for using bromine in water. Instead, you can use the N-bromosuccinimide with DMSO, which is a polar aprotic solvent that we've talked about before. But then we have a bunch of the polar protic solvent water in there to do the reaction as the nucleophile. What the N-bromosuccinimide does is it generates Br2 inside the reaction. So when you put Br2 in with this, there's a tendency for it to do halogenation, and we just add across. But if we generate the Br2 in a low concentration, then we'll form that bridged halonium ion, but there'll be so much more water that will form the bromohydrin. So it produces the Br2 in low concentrations, and that's the reason that we like to use it. We're going to see NBS used a little bit later in a different chapter on radicals. As far as the halohydrin formation, like halogenation, it does anti-addition because we form a bridged halonium ion, and then water comes in as the nucleophile, the backside attack, SN2 reaction, and we get halohydrin formation in anti-addition. So if we take cyclopentene here and we use bromine and water, we're going to get the trans enantiomers for this. Now, as I've mentioned before, because we have an achiral starting material, our products either have to be achiral or a racemic mixture. And in this case, we get the racemic mixture of a pair of enantiomers. And they are definitely the trans products. Now for halohydrin regiochemistry. When we were looking at halogenation, where we added 2 halogen atoms across the carbon-carbon double bond, we didn't really worry about the regiochemistry because we were adding the same atom to both carbons. But when we have unsymmetrical alkenes and we're adding two different things, in this case a halogen and OH, we're going to find that we get an interesting result. The nucleophile, H2O in this case, is going to attack the more substituted carbon. So the bromine, again, does the bridge bromonium ion in this case, and then the H2O is going to go as a nucleophile and attack the more substituted carbon. As a result, our OH ends up on the more substituted carbon. This is unusual for SN2 reactions for the nucleophile to go to the more substituted carbon, but it's something that we have seen with SN2 mechanisms. We've seen that in Chapter 9, Section 16, so if you want to go back and look at that, it has the argument and it has pictures of the transition state that explain why it does this. And we saw that with acid catalyzed epoxide ring opening. So you can go back and look at that. But I'm going to sort of rehash what it is, why it is we get the substitution at the more, where we get the nucleophile going to the more substituted carbon. So as we saw with the acid catalyzed epoxide ring opening, the nucleophilic attack is going to occur at the more substituted carbon, and the reason for that is that we have a partial positive charge on that carbon at the transition state. So again, we forward the bridge bromonium ion in this particular case. That nucleophile comes in, and because of the nature of this ion, when we're forming that new bond, we do get a partial positive charge on that carbon. And since that carbon is more substituted, that means that we're going to end up with the nucleophile going to the more substituted carbon. And then we have that deprotonation step that we see in lots of other reactions. So as far as how we can use halohydrins in synthesis, here is an example of a compound. We'll take this, the steroid, and we can do the halohydrin addition across the carbon-carbon double bond, and we'll get this. And then we can do the trick that we learned back in Chapter 9 for the formation of epoxides. We treat this with a strong base, deprotonate it, do an intramolecular SN2, and form the epoxide. And then in one very clever step, we can go from this to this. And think about what reagent might do that and look at what's going on. It says one step here. We have a methyl group here, but then the methyl group ends up over here. And so that is a 1,2 alkyl shift, a methyl shift to be specific. So it's a rearrangement. Very, very clever. Very, very clever. So in any case, the halohydrin synthesis is a very very useful kind of synthesis in any number of different synthetic pathways. Okay, so now for the summary of our halohydrin formation, there are 3 steps. The first step is the formation of a bridged halonium ion, and that is the rate determining step. There are no rearrangements that occur in that reaction when we do that. And see, the second step is the attack of the nucleophile, water. And then the third step is a deprotonation step, which is just sort of almost a throwaway step. The electrophile will end up at the less substituted carbon, and the nucleophile will end up at the more substituted carbon. And we do get anti-addition because of that bridged halonium ion. So now we want to look at number 28 on our in-class assignment. All right, so we want to draw the products for each reaction and indicate their stereochemistry. So this is NBS, DMSO, and H2O. So this is going to be halohydrin formation. So we'll just draw one of the enantiomers to start with. So we'll get Br, and then OH will be anti to that. And then our other product will be the enantiomer of that. And so I'll put Br and OH there. So we will get a racemic mixture of enantiomers. Again, achiral starting material. That means we're either going to have achiral products or a racemic mixture. So that will be racemic mixture. All right, here on part B, we need to take into account the regiochemistry that we just talked about a few minutes ago. And just as a reminder, the halogen is going to end up at the less substituted carbon. So let's go ahead and draw that. I'll put the chlorine like that, which means that our OH is going to be trans to that, and then our methyl will be a wedge coming towards us. All right, as far as the other product, it will be the enantiomer of that. So we're going to switch the stereochemistry at each of those. So the chlorine will be going away. Our wedge will be the OH, and our dashed one will be the CH3. And so these are enantiomers of each other. This is a 50-50 mixture because it's achiral starting material. We're going to have racemic mixture. Okay, so let's go back. And we're going to look at our last type of reaction with alkenes, and that is called hydroboration followed by oxidation. And the reason we have this hyphenated is that we do two distinct steps when we're doing this reaction. So it's a two-step synthesis sequence. It's not a two-step reaction. It's a two-step sequence because we're adding something at a different stage. The first step is to the addition of BH3 across the carbon-carbon pi bond to form what we call an alkyl borane. We're going to talk about boranes here in a little more detail just in a bit. And then once that reaction is complete, we don't isolate this because it's fairly reactive. We're going to take it and add another reagent, which is hydrogen peroxide with hydroxide in it, and that will oxidize the carbon-boron bond and give us a carbon-oxygen bond. So the first step, addition of BH2 across the carbon-carbon pi bond, and then oxidation, where we convert the carbon-boron bond into carbon-oxygen. Here are a couple of examples. So here we've got the cis-2-butene. We add it across and then do the oxidation, and we get this alcohol. In a very similar fashion with the cyclohexene, we get the borane and then oxidize to get that alcohol. And at first glance, you may look at this and think, okay, we're adding H2O. The net result is that we're adding H2O across the carbon-carbon double bond. Why not just do hydration? Well, there's an interesting twist to this that I will get to in a few minutes. But before we do that, I want to talk about borane just for a few minutes. So borane, BH3, is a very, very reactive gas, and it's a little bit difficult to work with in the form of BH3. In fact, in the gas phase, it's not really BH3, it's the dimer diborane, B2H6. Well, I'm going to show you something about diborane. This is interesting enough that I'm going to switch over to our document camera here for just a moment. And I'm going to draw the structure of diborane. So it's B2H6, and if H6, and if you attempt to start drawing structures of this, you immediately run into a problem. So boron, All right, right away, you may be thinking, what? What are you talking about? And then this is tetrahedral, so this hydrogen, one's coming forward, one's going back. All right, so this hydrogen, these two hydrogen, boron, that boron, and these two hydrogens are all coplanar, and these two hydrogens are above and below the plane of the other 6 atoms. Now, looking at this particular bond, it would appear that we're violating the octet or duet rule with hydrogen by having 2 bonds going to that hydrogen. Well, this is actually a different kind of bond. This is what's called a 3-centered 2-electron bond. There are 2 electrons that are shared across this entire 3 atoms. And so that hydrogen is held to both of the borons with 2 electrons. And that's what makes it different. It is unusual, and in most situations you wouldn't want to draw this. There are a couple of other ways that people draw this, but those are mostly not relevant to our discussion, other than to say it's a very interesting compound. And so I will go back to our screen and stop talking about diborane. Now, often, instead of attempting to use BH3 or B2H6 in the gas form, which is extremely reactive, we can take a commonly used solvent called tetrahydrofuran, THF, which we've talked about before. It is a polar aprotic solvent we've discussed before. And we can mix the borane with the THF, and when we do that, we get this complex between the BH3 and the THF. BH3, there's an unused empty p orbital on the boron, and that empty p orbital will react as a Lewis acid and accept the electron pair from THF, and that's what gives us this unusual structure. All right. So, and then when we do that, this is, like I said, a very useful reagent. Instead of having to work with a tank of gas that has the diborane, which again I mentioned is very reactive, you can purchase this in liquid form in solution from chemical manufacturers. So it's an easy chemical to get. Now, one of the interesting things about this reaction is that the BH3 does syn-addition across the carbon-carbon pi bond. And so that means that the hydrogen and the boron add on the same side of the carbon. And the implications of that will be a little bit more clear in just a few minutes. All right, so here is the mechanism of doing that syn-addition. This is an unusual mechanism, something that we have not seen before. And so it's a four-centered transition state. But we're going to take the sigma bond between boron and hydrogen, make a new bond with this carbon, and then we'll take the pi bond and make a new bond with this boron. So in the transition state, we're breaking this sigma bond, breaking that pi bond, and making these 2 sigma bonds. All right, so one step to do that reaction. And again, we call that a 4-centered transition state. Now, one quick thing about alkyl boranes, and that one quick thing is kind of interesting. When we add borane to an alkene, we'll form what's called an alkyl borane. And in principle, the alkyl borane, we oxidize it and form our alcohol. However, it turns out that alkyl borane is a little bit more reactive than borane is to begin with. So, since it's a little bit more reactive, it can in turn add to another alkene, and we'll get what's called a dialkyl borane. Well, it turns out that dialkyl borane is even more reactive than the borane that we started with. And so it can add again, and we can get what's called a trialkyl borane. And you may be wondering, where does it stop? Well, this is where it stops. So often when we say, oh, we do hydroboration, really what we're doing is we do it 3 times total, and we get this trialkyl borane, and then that is what we oxidize. So we have to add enough oxidizing agent to oxidize all 3 of those bonds. No big deal. It doesn't really change much of the math that you do when you're doing the stoichiometry, but it is kind of interesting. Now, when I say that, this is even more reactive. Some chemists have taken advantage of that to make another possibility, and that is an alternative to borane. And that alternative is called 9-boro-bicyclo 3.3.1 nonane, and the short name for it is 9-BBN. And so as far as what do you need to memorize the name 9-BBN, and it is essentially a dialkyl borane that comes right out of the bottle, and it's easier to work with. So that's why we like that dialkyl borane. All right, so there we go. That is our alternative to just regular borane. Now, this is the interesting part of hydroboration. So when we have unsymmetrical alkenes, we'll find that the boron atom is going to be bonded to the less substituted carbon. When we did this with just halogen, when we did halogenation, we knew we got trans or anti-addition to get the trans product on like cycloalkenes. But something interesting is that it didn't really matter what the alkene was. It didn't really matter what the what carbon the halogen went to, because it was just adding another halogen. But on this, it adds where the hydrogen goes to the less substituted carbon and the boron goes to the more substituted carbon. And so that is the only product that we form. Now, why is that? Well, there are 2 explanations for this. The first explanation is that the larger boron atom tends to go to the less sterically hindered atom, so it goes to this one instead of going to this one. I'm not sure that that is the best explanation, so I'm going to show you the other explanation for this, and that other explanation is an electronic argument. So this can help to explain the regioselectivity. Here, if we add the hydrogen going to the less substituted carbon and the hydrogen going to the more substituted carbon and the boron going to the less substituted carbon, here's our four-centered transition state. And it seems to indicate that there is a little bit of negative, a partial negative charge on that boron and a small partial positive charge on that carbon. And so we end up getting this product. If we look at the opposite, the one that doesn't happen, we would get the partial positive charge on the less substituted carbon. So because there's a partial positive charge, the more alkyl groups there are, the more it stabilizes this transition state. So because we have a partial positive on a secondary carbon instead of a primary carbon, we're going to get preferentially that secondary, this transition state will occur, giving us that particular product. Now, whether this is true or the steric argument is true, that there's a lot of people who argue about this, and that's a good thing. But here is the magic of the whole thing. Remember, in normal Markovnikov addition, the hydrogen goes to the less substituted carbon. Well, the hydrogen goes to the more substituted carbon. And so this is opposite regioselectivity from regular hydration. Let me explain in a little more detail. All right, so let's look at the final oxidation step to help understand what I mean by the hydrogen goes to the more substituted carbon. So the alkyl boranes, if you try to isolate those, they react with water. They react with when they're exposed to air. There's all kinds of things that they react with. If we take them and we put them with basic hydrogen peroxide, so hydrogen peroxide mixed with a little bit of this strong base, we get oxidation of the carbon-boron bond to form a carbon OH bond. All right, so one of the cool things about this particular reaction is that when you do it, any stereochemistry that is at this stereogenic center, if there happens to be a stereogenic center in whichever one you're looking at, that stereochemistry is retained. So when we oxidize that, we retain that stereochemistry, which means, well, it means that our configuration doesn't change. All right. And since it does syn-addition, and we are able to add the hydrogen to the more substituted carbon and the boron to the less substituted carbon, and therefore the OH to the less substituted carbon, we refer to this as anti-Markovnikov addition. So let me show you here an example of this anti-Markovnikov. So so here we've got hydroboration oxidation. All right, so the hydroboration oxidation and the synthesis of this compound, this drug that's called artemisinin. I had to look that one up as far as the pronunciation goes, but that is correct. Now, one of the key steps in there is we want to hydrate, add OH across this carbon-carbon double bond, but we want to do it in an anti-Markovnikov way where the hydrogen goes to the more substituted carbon and the OH goes to the less substituted carbon. And so when that happens, we get this. Now here it says several steps. And again, whenever you have several steps and it looks like a much more complicated molecule, because it is a much more complicated molecule, that means that somebody spent a long time doing these several steps. So you can make this in significant amounts. Now, this is a natural product. It is something that is derived from a plant, but if you wanted to use that plant to get this, you would have to, chop down whole, forest of this stuff in order to get a usable amount. So usually what they do for this kind of natural product is they use this as a source, a discovery source, but when it comes to actually having medicine that we're going to use in trials and use for people who have malaria, you have to synthesize it. So, all right, so here is our summary of hydroboration followed by oxidation. First of all, the addition of hydrogen and BH2 across the carbon-carbon double bond is concerted. It is a one-step process, and that means that no rearrangements are allowed to occur. And then the oxidation, when you get the oxidation, if you have a stereogenic center at the BH2, the OH replaces it with retention of that configuration. As far as regioselectivity, the OH ends up on the less substituted carbon and the hydrogen ends up on the more substituted carbon. We refer to that as anti-Markovnikov, and we also get syn-addition. So let's look at what this means in terms of a couple of different problems. So we're going to do 31 and 33. All right, so here we've got one butene, and we want to see what product is going to be formed when we add BH3 followed by the oxidation All right. Well, we're going to add the H and OH across that carbon-carbon double bond in an anti-Markovnikov fashion. So instead of getting a secondary alcohol, we're going to get this primary alcohol. And that's pretty cool. All right, for this next one, so the OH is going to go to the less substituted carbon, so our OH will end up over here, and then the hydrogen will end up over here. Now, one thing that you may or may not remember from a few minutes ago is that we get syn-addition and we get retention of that stereochemistry. So we'll get the CH2, CH3. There is an implied hydrogen here, and then OH is on there. So the OH and the hydrogen are on the same side of that ring. Of course, because this is an achiral starting material, we're going to get a racemic mixture. So we will draw the other products. Wedge, CH2, CH3. Again, there's an implied hydrogen that is a dashed line there, and we'll get that. So we'll get a racemic mixture of these two enantiomers. All right, for this one, we're also going to get anti-Markovnikov addition. So the OH is going to end up here, and we get syn-addition. All right, so this stereogenic center is going to stay the same, so CH3. That'll be a wedge. And then as far as this one of our products will be the CH3. There's an implied hydrogen there. And then OH will be cis to that hydrogen. So it'll be trans to that methyl. All right. The other product, all right, so we get this doesn't change. That CH3, the stereochemistry here doesn't change because we're not doing the reaction there. And then here we're going to have a wedge for the CH3. Hydrogen is the implied dashed line, and then OH is there. All right, so those are the two products. I want you to think for a moment what the relationship between these two compounds is. Just think about it for a second, and then I'm going to tell you what that relationship is. All right, now that you've had a chance to think about it, we knew on the previous one we had a pair of enantiomers, but on this one, these are diastereomers. All right, so they are stereoisomers that are not mirror images of each other. You may remember this from chapter 5. If you have at least one stereogenic center that's the same and at least one that's different, all right, then that is going to be a diastereomer. And in this case, these are diastereomers. We have one that's the same in both and two that are different. All right, let's look at 33 here. So here we're looking at the difference between doing hydration and then the hydroboration. So I will use a 1 with the circle to indicate the hydration. So 1 with the circle, and then I'll use 2 with the circle to indicate the hydroboration, followed by oxidation. So with hydration, with the acid, we're going to get regular Markovnikov addition. And so our products here would simply be we get the methyl there and then OH. And then our hydrogen that we added is on that CH3. It's one of the hydrogens there. For the second pathway, which is the BH3, so it's 2 steps, BH3 followed by the oxidation and base. We would get the anti-Markovnikov addition, And so the OH would go onto the less substituted carbon, and the hydrogen would end up on the more substituted carbon. And so that's the product we would get there. So now that you've seen that, you can probably do these other two on your own. So if you want to try that, pause the video for a second, and then you'll see me do it here in just a second. All right, now that you've paused the video and you have now come back, hopefully you've done this. So for hydration, again, Markovnikov addition. The hydrogen would go to the less substituted carbon, and the OH would go to the more substituted carbon. And so we would get that tertiary alcohol. So hydrogen comes out here, and the OH goes to that carbon. As far as our other product, our other pathway, in this one, we get anti-Markovnikov addition. So the hydrogen goes to the more substituted carbon, and the OH ends up on the less substituted carbon. And so we get this. And these are, of course, constitutional isomers of each other. All right, now for this one, the Markovnikov addition for pathway 1. All right, so those things are all the same, and then we'll have a methyl and an OH here. So methyl and OH. Again, hydrogen ended up on carbon 1, and the OH ended up on carbon 2. All right, for our anti-Markovnikov addition, our OH ends up on the less substituted carbon, and the hydrogen ends up on the more substituted carbon. And here in this structure, that hydrogen is implied on carbon 2. For the last part of this chapter, we're going to be looking at organic synthesis. All right. And we're going to talk about a method of thinking that is called retrosynthesis. It is a way of solving problems where you think backwards. And so when you're trying to do organic synthesis, here I'm going to lay out kind of a simple way to do something that's really hard. And so, if I say here is a reactant and I want you in 2 or 3 steps to be able to get to this other product, that means that you need to remember a lot of reactions. So I'm going to encourage that you keep track of your reactions and sort of, study them as we go along, because you're going to need to remember these reactions when we go to later chapters, both in this semester and next semester. So the very first thing is, anytime we go through a chapter and you learn about a functional group and all the reactions that go with it, you need to learn all of those reactions. Like, what are all the things you can do with an alcohol? What are all the things you can do with an ether? What are all the things you can do with an epoxide? Also, I want you to remember, well, what are all the ways that you can make an alcohol? What are all the ways you can make an ether? And what are all the ways that you can make an epoxide? All right. And this is going to apply to every functional group that we look at. Once you've got this collection of reactions of the ways that you use a functional group and the way that you make a functional group, then you can kind of pool them together and you have quite a big toolkit for solving problems. All right. Also learn learn the properties of each kind of reaction. Like, what kinds of reactions is it capable of undergoing? And this will help you to extend and maybe solve problems of particular reactions that we haven't even seen, or at least not directly seen. So think about, is this compound, could it act as an acid? Could it act as a base? How strong of an acid do I need? How strong of a base do I need to, protonate or deprotonate? Also think, is this an electrophile or a nucleophile? And we know that electrophile nucleophile is closely related to the Lewis acid Lewis base concept. So if you're thinking in terms of, is this a Lewis acid or a Lewis base, you're also thinking in terms of, is this a nucleophile or an electrophile? All right. Is it an oxidizing agent or a reducing agent? We're going to be looking at oxidations and reductions in a lot more detail in a later chapter. I think it's chapter 12. All right. And you need to be familiar with these reactions, so you want to look at them over and over and over again. And by doing that, you are going to have a big collection of options as what kinds of reactions you can do. So let's look at an example of thinking retrosynthetically. We want to synthesize the compound 1,2-dibromocyclohexane, but we want as our starting material cyclohexanol. All right, well, if you think about it, there is no reagent that I know of that will directly convert cyclohexanol into 1,2-dibromocyclohexane all in one reaction. However, if you break it down into 2 or 3 reactions, there are many pathways to get from cyclohexanol to 1,2-dibromocyclohexane. All right, so you need to think retrosynthetically. So what I mean by that is think backwards. When you look at this 1,2-dibromocyclohexane, think, what kinds of reactions do I know that will produce a vicinal dihalide? All right, so what kind of compound would I have here that would produce a vicinal dihalide? Well, there was a reaction in this very chapter where we took a type of compound, think of the title of this chapter, and produced a vicinal dihalide. Also, what kinds of reactions do I know that could go forward to give me something that can maybe either give me this or, or a precursor to it? And so we know of a reaction that will take an alcohol and produce an alkene. And we know how to take an alkene and turn it into a vicinal dihalide. So it turns out in this reaction sequence, the synthetic sequence, we can do this in 2 steps. All right, so thinking backwards, we know that we can make a vicinal dihalide from an alkene using Br2, and that we can take an alcohol and use a strong acid like sulfuric acid to do elimination to produce a cycloalkene. So when we put these 2 reactions together, we can put them into a reaction sequence that looks like this. Cyclohexanol treated with sulfuric acid will give us cyclohexene, which is what we refer to as a synthetic intermediate. Usually synthetic intermediates are things that you can isolate, purify, and then go on and do the next step. So it's not like you take this, put it into a flask, and then add some bromine to make this work. That's not how that would work. You would produce this compound, make sure it's purified, characterize it, do all that stuff, and then add once you have that compound, add bromine, and you would get the 1,2-dibromo cyclohexane. Now, of course, it would be trans. All right, if we wanted to do cis, that's going to be a lot more difficult. But it would be trans 1,2-dibromo cyclohexane. But that probably doesn't matter for whatever application we're looking at. All right, so we now want to look at these problems, 55, 57, 59, and 72. We're going to start with 55. This is a lot of problems, but it is a worthwhile thing to do. All right, so the problem here is asking, what alkene can we use to prepare each of these alkyl halides? So what alkene can we use? And it's possible there could be more than one, but usually one is going to be more convenient or easier to use than the other. In this case, it's pretty easy because it's just bromocyclopentane. We could make that, and I'm just going to use a backwards arrow indicating that we're starting over here. We could use cyclopentene and then just add HBr across that carbon-carbon double bond, and we get that. All right, so that is how this particular problem works. So I'm going to encourage you before I go through and show you all these, I'm going to encourage you to go through and attempt these on your own. Most of these are pretty easy for this particular problem. All right, well, hopefully you have attempted these on your own. Again, I'm just going to draw a backwards arrow. For this one, we could take an alkene, the cyclohexene, and to get the dichloride, we would simply add Cl2. So we would do chlorination and get that. Now, it would give us the trans product, but that's okay because it didn't specify here which one we wanted to get. All right, to make this one, we're just adding a bromine here. And since we're starting with an alkene, HBr is probably going to be our reagent. And we'll pick one of these. All right, and when we add HBr across that, the hydrogen's going to go to the less substituted carbon, and the bromine would go to the more substituted carbon. So we would get that tertiary halide as our product. All right, for this one, an alkene, pretty simple. We're going to get that 2-hexene. All right, and simply adding Br2 to that would give us this 2,3-dibromohexane. All right, for this next one, there's more than one possible way to do this. So I'm going to show both. So again, we're synthesizing that particular compound. So we could have the double bond here, and if we have the double bond there, all right, hydrogen would go out to this carbon, and then the chlorine would go to this more substituted carbon to give that as our product. Or if we used this 1-methyl cyclohexene, then we could get then we could add HCl across this. And by adding HCl across this, the hydrogen would go to carbon 2, and the chlorine would go to carbon 1, and we would get that as our product. All right. For this one, I'm going to redraw this one as a skeletal structure because, one, I like skeletal structures. All right, so we've got this tertiary. All right, so we've got that tertiary compound. And it doesn't matter where we put the double bond, because all of them are going to have the same double bond. And so I will just choose this one. 1, 2, 3, 4, 5. All right, and then if we choose HBr, and we add that across this double bond, the hydrogen will go to this carbon, and the bromine will go to carbon 3 on that chain. And that will give us that particular product. All right, let's go to number 57, which is our next one here on the next page. All right, draw the constitutional isomer formed in each reaction. So here we've got this particular alkene, and I'm going to sketch that one out as a skeletal structure. So 1, 2. All right, and then there's the double bond. And then, so there's CH, CH2, CH3. And of course, when we add HCl to this, the hydrogen is going to go to the less substituted carbon, and the chlorine is going to go to the more substituted carbon. So the product that we're going to get is going to be, let's just draw this out, 1, 2, 3, 4, 5, 6. And then on carbon 3, we're going to have another ethyl, and then we will have a chlorine. We'll have chlorine. Okay, so on this next one, we're doing hydration. I'm going to move it over here. When we do hydration, again, let me go ahead and draw this out, what it looks like. So 1, 2. All right, and we're going to add water across. Markovnikov addition, so the hydrogen will go to this carbon and the OH will go to this carbon. So our product will look like this. All right, if I were going to draw this out, if somebody gave me this compound and said draw it out, how I would draw that out is it would be equivalent to this. So those are the same thing. So those are the same thing. All right. And you can convince yourself that that's true, but it's what, 3-methyl-3-pentanol or 3-methyl-pentan-3-ol to get the proper nomenclature. All right, on this one, let's go ahead and I'm going to draw that one out again as a skeletal type structure. So yeah, carbon, double bond. So CH3, carbon, double bond, CH, and then CH3. So when we do hydroboration, remember we get anti-Markovnikov addition. So the hydrogen is going to go to the carbon with fewer hydrogens, and the BH2, which will end up getting converted into OH, will go to the less substituted carbon. So in this particular compound, we would get that. And that would be a good way to draw that structure. All right, on this one, so here we've got a cycloheptene, and it's always kind of fun attempting to draw a cyclohex or heptyl ring. So there's one, and then 2. All right, I'm not going to win any prizes for most beautiful structure, but we are going to have chlorine, so 1,2-dichloro, and I am going to indicate that it is the trans. And it says constitutional isomer, so we could just put that, but I'll go ahead and put plus enantiomer. So it'd be 1,2-dichloro. You wouldn't necessarily have to give the stereochemistry on that. On the next one, by the way, we're talking about stereochemistry, so that'll be fun. All right, so here we've got Br2, H2O. Again, the best way to do this is to know right away what that does, and that's going to give us a bromohydrin. And so we'll get the ring, and when we do the bromohydrin, remember the OH, which is the nucleophile, goes to the more substituted carbon. So we will get OH, and then Br ends up on the less substituted carbon. And so that would be our product there. All right, just as a reminder, 9-BBN is just a substitute for borane. So just treat it like it's just regular borane. And hydroboration followed by oxidation, that does anti-Markovnikov addition of H2O across a carbon-carbon double bond. All right, so with anti-Markovnikov addition, we're going to get the OH out there. So OH out there. So hydrogen goes to this one, that's implied hydrogen, and then the OH ends up on that particular carbon. All right, NBS, this is going to be formation of a bromohydrin with NBS, DMSO, and H2O. Again, when we're forming a bromohydrin, the nucleophile, which is the water, is going to go to the more substituted carbon. So we will end up with the bromine going out here, and then OH, we'll just kind of squeeze it in there. It goes out, it goes right there. And then finally with this one, we're adding bromine, so we're going to get a bromine on one and a bromine on that other carbon. So not a beautifully drawn structure. If I were going to draw this structure and this one, if I were going to draw this, I would draw it like this. If somebody just told me what this structure was. So I have bromine there and that. Same thing here. So those are, this is equivalent to that, and this is equivalent to that. All right, stereochemistry. This is kind of fun. And by fun, I mean it's challenging. This is a challenging problem. Well, in any sort of reasonable universe, I would have made this have more space so that you would be able to draw these all out. But just bear with me. So here, bromine does anti-addition. So we're going to add 2 bromines to this. And I think it's easiest to draw the carbon-carbon bond and the 2 bromines, and these are in the plane of this paper. All right, and so we're treating this as if the bromine comes in from the top, and then the other bromine is going to come either from the bottom, from the left side, or to the right side. It doesn't really matter in this case which one it goes to. We will end up with 2 different products. If the bromide comes in from the bottom, then we're going to have this cyclohexyl as a wedge. And I'm going to attempt to draw this without drawing something hideous there. And then hydrogen. So this is cyclohexyl. It's coming towards us. The hydrogen's going away. And then on this one, that methyl is going to be going away, and the hydrogen will be coming forward. All right. Then, if we take that, the other product that is formed, all right. So if we draw the bromine, the anti-addition of the 2 bromines like that, and then we're going to do the same arrangement. So the cyclohexyl is going to be coming towards us, and the hydrogen's going away. And then here, the hydrogen is coming towards us, and the CH3 is going away. So, these 2 are hydrogen and CH3. They're both going to be going away from us in both of these products. And then the cyclohexyl and the hydrogen here are both going to be coming towards us. Here's that one, and there is the hydrogen. Okay, so on this next one, we're forming a chlorohydrin. And with that chlorohydrin, there's 2 different ways this could work. But on both of them, the chlorine is going to end up on the less substituted carbon. So we're going to add chlorine and then OH across this carbon-carbon double bond. Let's do it one way, like this, where the chlorine is there and the OH is there. Again, these things that are on the bottom are going to be coming towards us. So we've got hydrogen that's coming towards us, and this methyl will be going away, and this ethyl will be coming towards us. So CH2, CH3, and that other methyl will be going away. All right. For the other structure, again, we need to make sure that the chlorine and the OH do anti-addition, but also that the chlorine ends up on that less substituted carbon. So here we're going to put the chlorine out there and the OH right there. So hydrogen will be coming towards us, and then this ethyl will also be coming towards us, but let's do the methyls. So the methyl will be going away from us, and then this ethyl will be coming towards us, and that CH3 will be going away from us. All right, we've got one last structure here, NBS, DMSO, and H2O. This is going to form a bromohydrin, and just as a reminder, the H2O is the nucleophile. It'll end up going to the more substituted carbon. So we'll have bromine, OH, and then again, the things that are on the bottom, we're going to make those come towards us. So we'll have a wedge, hydrogen, dashed CH3, and then CH3, and then CH2, CH3 as the dashed line that's going away from us. All right, and the enantiomer of that All right, so again, the ones on the bottom are going to be the wedges coming towards us. So hydrogen, CH3, and then CH3 is coming towards us, and that ethyl is going away from us. I recommend going through, if you have your molecular models, I recommend looking at the molecular models and then kind of visualizing where the halogens are going to end up and the OHs are going to end up. And then I also recommend watching this part of the video again, because this is a tricky topic. All right, that gets us down to our last problem, number 72. And number 72 says, devise a synthesis for each of these. All right, well, I will tell you that there is more than one possible synthesis for each of these, but I'm just going to show you one example. So there are, like I said, many possibilities here. We could do, we could convert this into a halide and then convert it into an alkene, but we know that if we can have this as an intermediate structure, so 1, 2, 3, 4, 5 carbons, if we have this as an intermediate structure, all right, I had to pause the video there for a second. There were sirens, a helicopter, and a plane that all seemed to come over all at the same time, so I had to pause. This as our intermediate structure, that alkene. So we know how to take an alcohol and turn it into an alkene. Using sulfuric acid. All right. And at the same time, and then subsequently, we could do H2O with H2SO4, and then that would give us that alcohol. And that is one of many. You could also take this and turn it into an alkyl halide and then turn it into an alkene. But the alkene is the key feature here. All right. Now, when I give you a problem like this on an exam where I want you to write it out, one of the things that I'm going to recommend is that even if you don't remember the reagent, write down the sequence, because you will get partial credit for getting the right sequence of reactions. You will also get partial credit if you know the reagents and you get them out of sequence. You can get some partial credit that way. To get full credit, you do need to have a viable synthesis where each step works and the right thing. And it doesn't have to match mine perfectly. It could be a different sequence of steps. That's fine. All right, so we'll take this one, and we know on this one, our intermediate here, this one is pretty easy. Since this is a chapter on alkenes, not surprisingly, we're going to have an alkene as an intermediate. We know that we can take this and eliminate it using a strong sterically hindered base. So I'll redraw that, and we could use something like potassium tert butoxide. All right, and that would give us that alkene, propene. And then we could add Br2 to that, and that would give us that dihalide. All right, in a similar fashion here, we could form an alkene and our alkene intermediate, again, with propylene or propene, if you want to call it that. So we could take this alcohol, use sulfuric acid to generate that alkene, and then we could use methyl alcohol, CH3OH, and H2SO4, and do an addition across that. This would be just like hydration, but we're using alcohol instead of water, and then that would give us that product. All right, on this one, I think it is useful to draw out what that compound is using our skeletal type structure. So there's the CH3, 2, and there's the CH3I. All right, without even thinking about what the reagent is, you can come up with an elimination that you could do between these. There's any number of reagents that you could use, but you could form isobutylene, and then you could simply add across that to give us that chloride. So this, you'd use a strong base. I'm going to use my favorite, which is the potassium tert butoxide. All right, and that would give us the isobutylene. With the isobutylene, we could react that with HCl. It'll do Markovnikov addition, so the hydrogen will go to the less substituted carbon, and the chlorine will go to the more substituted carbon, and so we'll get that tert butyl chloride as our product. All right, this next one, not surprisingly, our synthetic intermediate is going to be an alkene. So converting this into an alkene, again, using a strong base. I'm going to use my favorite. So potassium tert butoxide, that would give us the alkene. And then from that alkene, we could do Br2 and H2O, Alternatively, we could do NBS, DMSO, and H2O. That would work as well. And that would give us our bromohydrin. Now, as far as for practical purposes, this is going to give us trans, so we would get the trans product. Getting cis would be challenging. All right. And then here, this is cool. So as a synthetic intermediate, here we've got an alkene, and we want to turn it into an alkyne. Well, there is not a convenient way just to remove those two hydrogens. I mean, there are some tricks you can do, but they're kind of iffy. So as an intermediate, we're going to be looking at something like this. And you could do a dichloride, but I'm going to do the dibromide because, make it rain, I guess. So we will take this, which is that propene that we started with, and we'll add Br2. And we'll get 1,2-dibromo propane. And then back to the favorite base, we're going to go with the strong sterically hindered one. And we'll use 2 equivalents of the potassium tert butoxide. And that would give us that alkyne. That would give us that alkyne. If you wanted to draw that alkyne as just a skeletal structure, it looks like that, which that can be a bit confusing, but this is equivalent to that. All right. Well, that is the end of chapter 10, and coincidentally, chapter 11 is all about alkynes, and so that is what we will be looking at next time when you see the first section of chapter 11.